Hello and welcome back to another coding related video with Mr. Jacob. Today we will take a look again at our RustBrain Brainfuck interpreter, which we wrote in videos before to interpret Brainfuck. The ultimate goal there was always for me to in the end create some sort of JIT compiler for it, because I've never done that sort of stuff. I've worked in teams where things like that had been done, but I've never really wrote code related to that or really worked with that part of the code base. So I decided it would be a nice thing for me just to show to me that I actually can, and to work out the ideas behind that, to do something like that. And I decided maybe it would be a nice idea to do this together with you. Yeah, it was a nice idea, but unfortunately, while recording the videos doing exactly that, writing that JIT from scratch, I had to realize that I wasn't fit enough in that topic to actually do a live coding session of that. I have about 6.5 minutes of video where I developed this thing, and it can't really be cut down to much less without completely destroying the coherence of the video. So I decided to give you an overview and talk about what I did after the fact, because I wanted to present to you what actually would something like a Brainfuck JIT look like. So yeah, I would say let's get right to it, because I needed to look up a lot of different stuff you will see in a second. It wouldn't have been a good idea to do that live. But yeah, let's dive into it, and I will give you an explanation of what I have done and essentially how I have done it. Of course, I could now, after I know all these things I know now, I could have essentially reverted the repository back and recorded a live coding session exactly implementing this kind of stuff with you, now that I know exactly how I would do it. But I guess that would destroy the spirit, and I don't want to do that on this channel. If I'm showing you a live coding session on this channel, it is a live coding session, and I have not done specifically this thing before. So yeah, so let's dive in. First thing you will notice here is this is our usual Brainfuck interpreter, and I can show you this easily by simply going to this thing on my system and do a cargo run examples. Yeah, and there we are again with my cargo completion. So examples / hello world Brainfuck, which is the Brainfuck example from the Wikipedia. And as you can see, yeah, we get some warnings there. We don't really care. We get the output that the Brainfuck example is loaded. The interpreter is used for execution, and there is the output that we would expect. And if we take a look at the example file, so it would be this one, we see that it is actually this and some more, which you can't see because it's behind my face there. So let me quickly scroll that up. It's a Brainfuck program. It's contained of things which increment the data in memory. It's using conditional jumps. It's moving the data pointer in memory. It has conditional jumps within conditional jumps, and it has backward jumps, and yeah, and all the neat little stuff. It has the output commands. The only thing that this one does not use is input, which we still haven't implemented yet. But yeah, that's actually it. So we have an interpreter which actually interprets our code. And to just get back to this, we have of course a tokenizer and all that stuff to parse it. But our interpreter essentially only takes a stream of instructions. It takes a list of instructions which our lexer already, or better said, our parser already created. And the parser goes ahead and combines multiple instructions. So if we have something like this, for example, it would be 1, 2, 3, 4, 5, 6, 7, 8 pluses, so it would be 8 increases of the current memory address. And that would actually be stored or created by the parser as an instruction increment with a count of 8 in this specific context. So we are actually interpreting those instructions. We are going through them, and once we are walking through them, we are actually capable of executing it, sort of. So what we are actually doing here is, for each of those instructions, and as you can see, there aren't that many, because Brainfuck is not that kind of a complex language, fortunately for us. We have something like address right, address left, increment, decrement, output, and so on. And we are simply executing the corresponding action once this instruction is encountered. So an address right, of course, makes our address go up the count. So if we want address right of 8, so we want increment the address by 8, we simply increment the address by 8, and we walk one instruction pointer to the right, because now we want to actually process the next instruction. Same thing for something like increment, which we saw in the example. We are taking the memory, which simply is an array, at the address, which is currently the address, and we are actually adding to this memory the count we were given, and so on and so on. Output is not that much different. It simply goes and writes the current byte at the current memory address to std out. There we are. Jumps are a little bit more involved, because jumps have the problem that we have during the parsing phase. Let me show you that. Parse. There must be some sort of parse instruction. Yeah, exactly. So if we are actually matching, there we are, matching a token which is a forward jump, we are actually creating something within the instruction stream. We are creating a jump forward here to jump forward to instruction counter 0, which isn't correct yet, because we haven't seen where the jump ends yet, because a jump is always something between those angle brackets. So between this thing, for example, and this thing here. So at the processing time of this, we don't know where this exactly is. So what we do is we actually mark ourselves the position of the forward jump point, and once we encounter the back jump point, we actually take this remembered position and create the back jump, as well as back patch the forward jump so that it goes to the right direction as well. This will be important in a second when we are talking about the JIT. So yeah, that's actually what jump does. On the other hand, jump does, once it has this information during interpretation, it simply goes ahead and tells us that we are actually or where we should actually go. So we check the condition. So a forward jump is always if the memory, the current pointed memory address is 0, then do the jump. Otherwise, just go over the jump. And the jump back is always if the pointed to memory is not 0, then jump back, and otherwise go over it. So we are essentially doing this condition check here and then moving the instruction pointer accordingly. And that's actually all we need in the end to create a Brainfuck interpreter. But this video should not be about the interpreter. It should be about the JIT. So what we actually want to do now is we want to compile our Brainfuck program live within our execution into X86 64 code and actually execute that. And it should in turn then do the same work that it does now with the interpreter. How can we actually do that? First of all, I have refactored out the initial execution of the program. So after it has been parsed And after this stream of instructions has been generated, we are either using the execution here, which is the interpreter execution, which creates a new interpreter, gives it the program and calls run on it. Or if we are on an X86 64 system with the target Linux, in this case, this is important because we are using the Linux system ABI and the Linux system calls like write, for example, to output characters to the screen. And I didn't want to fiddle around with making this macOS compatible or Windows compatible or something like that. I just wanted some kind of proof of concept for the compiler that I could write. So the easiest way there was to target Linux, because I can easily create an x86 64 container on my macOS ARM system here and work within that, which is running a Linux then. And if you are interested in that, check out the video where I do some experimenting on how to do that actually, and how to map, how to dynamically map. We will get to that in a second, but how to dynamically map memory in a way that we can simply put bytes in it, which would be the machine code to execute then, and then really execute that in Rust, because I figured that out in this experimentation session we did. Okay, so essentially what we are doing here then, we are printing that we are now using the JIT for execution so that we can see which branch of this code has actually been run. Then we are instantiating us a new JIT compiler. We are giving it the program and we are giving it something new, which is an x86 assembler. We will see that in a second. I wrote that as well. Then we are telling the compiler to compile, and then we are running and we are done. And in the main program now, I simply call execute. And based on these conditionals, which are mutually exclusive, so either this one can match or this one can match, we are either using the JIT or we are using the interpreter if the system and the target is right. Okay, so that's for now. So let's see what we can actually do with this JIT. So if I change to my x86 simulated environment here, which is an x86 Linux I'm in now, I can actually do something like examples, hello world, brainfuck, press enter, and as you can see, it now says using JIT for execution, and it prints hello world. But what did it actually do? And I have left in some debugging I had there, which allows me to see actually the byte stream that the system generated. So if I do hex dump, I think it's -C. No, it's not. Oh, there is no hex dump in here. Okay, let me quickly install that. DSD extra utils. Let's not utils. Let's quickly install that in the container because it seems that I'm missing that. So now hex dump -C. Output bin, which actually is the generated machine code to execute. So this is actually what lies within memory as a function and is then called by our code once it has been generated. So this is generated machine code, and we can actually disassemble that quite easily and take a look at what exactly instructions are in there. So if I take a look at that, it's doing some work there. So there are quite some instructions there. This is actually the translation of our Brainfuck program into machine code. So into x86 68 machine code. Something like reading the memory specified by an address within a register, in this case RSI, into the Rex accumulator, adding something like 8 to it. Wait, 8. Doesn't this look familiar here? 8 was the first actually that we had in examples hello world.brainfuck. It's actually that. It's actually those 8 address increment value increments here, which we are actually doing there. We are kind of incrementing memory there. How we are exactly doing that in machine code, we will see now in a second. But this is actually the compilation to machine code of the Brainfuck program we have here. With a little bit extra wrapper around it, kind of, we could easily make our Brainfuck JIT now a real Brainfuck compiler. So something that would take Brainfuck input and create an executable out of it with machine code in it, which is the compilation of the Brainfuck program. And I really like that. Once I had this running, I was really happy, as you can properly think. So let's take a look at our X86 JIT and let's take a look at what and how it works. So we have now here, we have some structures and enumerations and stuff like that in here, which I created. But mainly we have this assembler, which is actually something that we use to ease the creation of machine code, because we don't want to have the byte sequences everywhere once we are processing our instructions, because nobody can read that anymore. So actually this X86 mini assembler sort of, it only supports exactly the instructions that I need to assemble for this Brainfuck compilation. Essentially takes our sort of mnemonics. I didn't really do all of them, and I may not have done them perfectly correct in naming or things like that, but essentially we can give our assembler by calling specific functions, something like the equivalent of what I'm currently highlighting, like something like move into our RHX, the value that the memory address in the RSI register is pointing to. That's essentially what is there, and the assembler will then automatically generate this byte sequence and output it for us. That's essentially what the assembler does. We will take a closer look at that as well, but for now just assume that it does. It collects the code stream that it has emitted, and we can later on take it and do something with it. Then we have wait, JIT Compiler, where is... Didn't I move that? There, memory map executable code. That's exactly the function that we created the last time using libc and mmap and stuff like that to map a region in space, to allocate a region in memory which is executable, where we can actually put our dynamically generated code and then actually tell the system, the CPU, to execute it. And that's actually exactly what we developed within our experimentation video. So if you are interested in how we came up with that and how this specifically works, please take a look at that video where we actually live code that then. Okay, so I simply took that from our experimentations and copied it in here. I didn't change it anymore. So with a slight, I did one little change, but we will get to that in a second. So let's now take a look at our JIT compiler. So the thing that actually transforms our Brainfuck program into the bytecode stream. So as with our interpreter, we are allocating 640 bytes of memory, which we could somehow make dynamic. In the interpreter, this wouldn't have been a real problem. In the JIT, that would make things actually more complicated. We could do that, definitely, no problem, but it would make things more complicated because we would need to implement more syscalls for memory reallocation and stuff like that. Okay, so essentially what the JIT compiler holds during its compilation is it has the program itself. It has some sort of memory space, so some pointer to a region in memory where it is working, and it has some sort of address, which is essentially the memory address currently pointed to by the program. So this is actually held within this JIT compiler struct. So how are we now actually working with that? Yeah, essentially we are more or less doing the same thing than we are doing with our interpreter. We are walking through our program, but in comparison to our interpreter, we are not jumping around in the program and going back and forth and back and forth and back and forth. We are simply iterating from one side to the other. So we are doing one path and transforming all of those instructions into corresponding machine code. And how we are now actually doing that, and that is the interesting thing here. And the most interesting thing, I guess, is this. So how do we actually access the data within this structure, the memory and the address? Because that is essentially what our program needs to modify. We have operations which move the memory address up or memory address down. We have operations which increment data, a data byte in this memory, or decrement it. We have something that reads from this virtual memory space here and actually outputs that to the screen. And we have something that jumps around in our execution code in our memory space with the commands like that, based on bytes within this memory. So somehow our compiled program needs to access that. And yeah, essentially we can do that in the same way that any C compiler will do it. Okay, so let me explain to you how this actually works. So there is something, some specific kind of calling convention, because C calling conventions, POSIX, I guess, X86 calling conventions. So essentially there is some sort of rule set which describes how, when a specific function in memory is called, so if we are jumping into a routine, for example, that has been compiled from a language or that has been used in C specifically, that are the C calling conventions, but most other languages, like for example Rust can and a lot of others can to work with C compiled code. How this actually works, how this memory layout is used and stuff like that. So essentially what is happening here is, and I guess it is somewhere here, let's search for register, because I can never seem to find the, you can't be serious about that. Where actually, maybe I already jumped over it. It kind of describes which registers are used to pass parameters to the function. For example, if we are using only integers or only floating points, we can easily transfer those informations within registers within the CPU into our functions. So specific registers are set in a specific order for each of the arguments, and then the function is called. And then the return value for example, from a function is expected to be in a specific register as well, if you want to return something. If you have too many arguments, like there is no more space to fit in the registers, for example, the stack will be used, so the rest will be put on the stack. Or if you are using types which aren't supported there. So, but let's see if I can find the position that can't be C calling conventions parameter or argument registers. I mean, I could show you in my code, but I want to show you registers, the C calling conventions, the caller's rules. There we are, perfectly. To pass parameters to the subroutine, we put up to 6 of them. So we can actually pass up to 6 arguments to our subroutine into registers. And the order here is important. The first one would be RDI, RSI. then RDX, then RCX, then R8 and R9. So we can actually put something in there, and that is how the C calling convention works. And as you can see here now, we are actually in the end, when we are running the program, or when we are running the program, we are defining, when we are defining it, we are defining it as an extern C function. So a function with C calling conventions actually, which takes a pointer to a U8 construct array, whatever. So this is our memory array actually, and a pointer to a U size, so a 64-bit value in memory. So this is our address. So what I'm doing actually is, when calling this function, which is actually this line here, in the end, our JIT function, after we have created the bytecode and loaded it into memory at a place where we can execute it, I'm calling it with C-style calling conventions and putting in a pointer to our memory within our struct, as well as a pointer to the number holding which of those memory cells we are currently working on. And those will be passed, due to the C-style calling conventions, via, and let's see, the registers RDI and RSI. So RDI will be the memory address where we can find the starting point of our allocated memory array, and RSI will be the memory address where this address counter actually, where in this allocated memory array we are actually lives. So both of those are memory addresses and will be in those registers. And what we now actually can do, we can work with that. So what I now can do is, in case we want to actually move the address to the right, so we want to increment the address pointer to our memory by the given amount, I do the following. I first go ahead and move the real value. So I tell the system to look up what is at the memory location that is pointed to by RSI. So our second argument, which is the memory address pointer. So we are looking into memory at that position and taking a peek at what actually is the value of that. And we are putting that into our RAX register, which is the default accumulator. So we are just putting it in there and loading this value from memory, so to speak. Then we are actually executing an add. So we are adding the specified value to move to the right. In this case, I guess it was 8, will be added there. And then I will move back the value from rex into the memory location pointed to by the RSI register, which in turn is again the position of our virtual memory address there, of the memory of our Brainfuck program. And after we have done that, actually, I can show you how this looks. If I do something like examples, or let's quickly call it T, and we just do one movement to the right here, and we save that, and we now tell the system to go ahead and run T. No idea why it recompiled. I guess I changed something in the editor. Okay, now it has executed, and now we actually can disassemble quickly the output bin, which is generated. And now we see actually what code was generated, and that is exactly the code that you saw before. So that you just saw me generate there in code. So we are moving the memory, the value of the memory location this register points to, that is what the square brackets are here, into RAX. Then we are actually adding 1 to RAX. Then we are moving back the value from RAX into the location pointed to by RSI. And then we are actually returning, because we are a function and now we are finished. And exactly that machine code here does this operation. It takes the pointer to the second argument it was given. So it assumes the second argument is a pointer. It takes it, adds 1 to the value within this pointer, and then it returns. So this is actually more or less all the magic. And now we need to implement that for all of the instructions. So we are doing the same thing when moving left. It's exactly the same code, but with the difference that we are emitting a sub here instead of an add. So we are reducing the value by the given, the memory address by the given value. How are we actually incrementing something in memory? It's even less complicated because we can do it in 2 instructions and not in 3. And I'm not an X86 64 perfect coder, so there may be something in the instruction set that does this, what I'm doing here, more efficiently or something like that, or with less instructions. And of course, one could do some optimizations here, like I'm at a lot of points I'm loading things in EAX in Rex, for example, which are already there due to calls before, due to instructions before. But I've not done any of that. I just wanted to create assembly, so bytecode that actually does what the Brainfuck program does. I didn't want to optimize it in any way, and I don't think I really could with a lot of more work, because I don't have that much knowledge of X86 64. But in this case here now, we are actually going ahead and doing more or less the same thing. First of all, we are getting again the value of the memory address. And what we can do then now is we can actually emit an add directly on the memory. So we can actually emit an add call. We can emit, in this specific case, it's only an 8-bit value, so 1 byte. And there is a shortcut to do something like, I want to add something in memory with a specific offset. So what is actually done here is, what I'm doing here is I'm taking RDI, which we remember is our first given argument to the function that will be stored in the RDI register. And we are taking actually that, which is the base pointer to our Brainfuck memory space we allocated. So we are taking this base pointer, this starting point in our real memory, and then we are using the contents of the RUX register as offset into this space. And we are actually using it by offset of 1, so byte-wise, we want to go the offset count of bytes forward. Actually, you can specify that while emitting machine code. So there is actually a possibility to specify a scalar there, which then does something like, I want to always take this offset as multiplied by 8 and stuff like that. But we don't need that because we have a byte-wise segmented memory space there. So we are using just the offset. So we are going from the base pointer of our Brainfuck memory, the amount we loaded from the address counter before, forward, and then we are actually adding the corresponding value to that. Let me show you how this actually looks once we are done. So let's just do a plus here. And let's see how this actually works. This ASM minus 64 byte mode and output bin. There we go. So what we now have here is actually what I've just shown you. It takes again the contents of the memory space that RSI points to and puts it into RUX, and then it adds 1 byte, which is a specific instruction, to the memory content, so the actual memory address that is referenced by RAX plus RDI, so our offset plus our base address, and it adds 1 to it, and then it returns. So this is exactly the code that we create. For decrement, we do the same, but we emit a sub again. And then we have output. Output, as you can see, is a little bit more complicated, because output now, for the first time, needs to execute a syscall. So what we need to do is we need to go to the kernel and say, hey, kernel, go please ahead and take something from a specific memory location and output it to the screen. So write it to the file handle 1, which is stdout, so that it actually is shown by the console. And this is done through syscalls. There are a lot of different syscalls. You can have read syscalls, write syscalls. You can do memory allocation through that. So a lot of different stuff that most of all the basic stuff that you need the kernel to do for you, because you can't do that in user space. But if you compile something like that, it always generates syscalls, which are essentially a way to kind of interrupt the kernel and say, hey, I'm here, I want you to do something for me. And here are the corresponding information bits and pieces that you need to do that. And essentially, there is a specification for that, so how syscalls actually work. And in this call, in this situation here, we are actually, let's take a look at what we are doing here. We are kind of using the RDI and RDX and stuff and registers as well as rugs to specify what to do. So the first thing interesting here, and the only thing, by the way, why are they in this order, is because we need to do it in an intelligent way, because we are already using RDI and RSI registers for our transference of the pointers into the function when calling, and we need REI and RSI to be something else when doing a this call. So we need to kind of shift around some data before actually doing that. So that's why the order is not perfect there. But normally the first thing that you need to do is that you need to know is that the RAX register actually contains the number identifying the this call to do. In our case, we want to do a write this call. So if you want to do write, the corresponding number is 1. You can actually look that up. There are header files which show you that, or you can Google it or something like that. This is specific for Linux, by the way. This is the Linux syscall way of doing it. So it's the System 4 ABI, I guess, or System 5? No, System 5 ABI, and I'm not 100% sure, but this is actually the way that Linux does it. So if I wanted to do that on macOS, for example, I would need to change this specific code. The other code that I did with the memory manipulation and stuff like that would work fine, but this would need to be changed. It wouldn't be that much of a problem, but macOS has a little bit different kind of how it does syscalls. Okay, so first of all, we are loading the instruction into rex. This is write in our case, which is 1. Then in RDI, we are actually specifying where to write. So we can actually use this to write to a file, for example. There is a syscall for open, which returns you a file handle, and then you can put this file handle, this file descriptor, into here and write something into the file. So the kernel can go ahead and write something into the file and stuff like that. So, but in our case, we simply want the stdout descriptor, which is usually 1. Then we are loading the size of what we want to output. So the byte buffer length, more or less, we are specifying to 1 as well, because we only want to print 1 byte. That is exactly how Brainfuck works. It takes the byte at the corresponding Brainfuck memory and outputs it. So we want 1 byte. And then actually we are doing something else. We are loading the location to where this byte is. And we are doing this essentially in the same way we did it before. So we are first loading the offset, so the address, what we did before, which is an RSI, the address to the Brainfuck memory we are currently pointing at. We are putting this in RAX. Then we are adding the offset actually, so the memory offset of the base pointer to our Brainfuck memory, adding that to the rex value, because we need to have the full memory address to the exact memory pointer to the byte we want to read actually in there. So we are doing that in rex, and then we are moving rex to RSI. And we couldn't have done that before because our RSI usually is the pointer to our memory address. So we couldn't have done all that in RSI before. Maybe we could have actually, because... No, we couldn't have, because it's the pointer to the memory address and not the value of the memory address. Okay, so we are shuffling around some stuff here so that in the end, in RSI lies the pointer to the memory the kernel should take and write into the file descriptor 1. And what we are doing before doing all that, we are pushing the RDI and RSI values onto the stack. And after we are finished, we are popping them from the stack, just to ensure that whatever we are doing in here, or whatever actually the syscall does with our data, with these registers, which it actually doesn't, it only touches EAX, I guess. RAX, but yeah. But we can shuffle now data around like we want to. For example, we can put stuff here in RDI and RSI without thinking about it for the syscall. And after we are finished, we are just popping our old values, the pointer to the memory space and the pointer to the address back from the stack, and we are ready to do our next command here. And then we are actually emitting the syscall instruction. There is actually an instruction for that. So that then is used to tell the kernel, now go ahead, read all the information from those registers and do your thing. And once you have done that, you can come back here and tell me, okay, I'm finished, and now you can go ahead. So that's kind of a call to a function, but only kind of, but you can think of it like that. Okay, so this actually, how does this work, or how does this look in the end? So if I'm replacing this with a dot, which is output, and run it again, you can see that we have exactly those things here. We are pushing RDI, we are pushing RSI onto the stack. We are getting the real value of our Brainfuck memory pointer value thingy there. So where do we actually point at this moment in the Brainfuck memory? Then we are adding the base address here. We are moving the information to RSI. We are moving the write, the write specification, so what command to execute into RAX, which is 1. We are specifying the where it should go and how big it is, so what the length is into the corresponding registers. We do the syscall. We pop off again from the stack the RSI and RDI in reverse order, of course, so to get the right values there, and return from the function. So this is actually the bytecode which you can use to print a character to the screen, or better said, to write it to std out in Linux. So that is the bytecode for that. And then we have essentially jump forward and jump backward, which kind of does the same things that it did before, but in this case it simply uses compare instructions. So it does the same thing with the backpatching. So what it actually does here is it simply emits something completely broken. It emits a memory address which isn't a relative jump point, which isn't useful in this case, first for a forward jump. And once it sees the backward jump, it goes back and patches the jump target before with the right address. So once it has seen it, it knows where in the output byte stream it is, so it can create the correct address to where to jump. So if you're interested in that, all of the code is on GitHub. Take a look at it. I think it is quite understandable, but it needs some time to understand. What we are actually doing here is more or less is a compare. So we can do a compare which sets the 0 flag, which is a specific stored in a specific register. It's a CPU flag, which we can then use to jump based on if it's 0 or not. So we can actually do something like, if the value is 0, we want to jump, or if the value is not 0, we don't want to jump. And then we specify a jump target within the memory to which location relative it is, a relative jump to where we should jump actually. And using this technique, we can then jump in our bytecode stream, in our assembler stream, back and forth between those different jump points and execute the corresponding code. And once we have done that, we are simply adding this last, which we always see here, this return statement, and we are done. And once we have this code, we take it, we use our, in the last video or in the experimentation video, I'm not sure in which order I'm going to post them, code to map it as executable into memory, this bytecode, and then we execute it, giving it the corresponding pointers. And that's more or less all to the magic. This is more or less how this JIT works. So it simply goes ahead and creates for all of our Brainfuck instructions, it creates X86 64 bytecode, which essentially throws around stuff in memory and adds and subtracts and goes ahead and does this calls to achieve what we want it to do. And yeah, and in the end, this is it. Now let's take a quick look, only a quick look at what the assembler does that I've written. First of all, it names our registers because I can never remember the order of the registers, the byte order, so to speak, so how to address them and stuff like that. All of that can be found in the X86 64 specification. You can get it there and you can figure it out there. That is only to make things more readable. But then we have something like, we are actually implementing, let's actually take a look at implementing mof, because that is the most used command. So it always takes two operands, and operands can be something like, they can be a register, so a specification of which register to use as a source or as a destination. They can be an immediate, so a 64-bit value. Maybe this should be called immediate 64. I don't care. So a specific value. So this is, for example, something that we used in an add call to add to the memory address pointer to take it, because that can be more than a byte actually. We have an immediate 8, which is only a value which is up to a byte. We need that because there are certain instructions which explicitly take only a byte as an immediate and not a longer value. We can then reference kind of the value of memory pointed to by a specific register. That is what you always see in the mnemonic code as that. So as this square brackets, essentially, that's memory by register. And then we have memory by register and offset. You have seen that as well. So it's kind of dereference what's in there, but take a base pointer and offset into it. And based on those, for example, we want to put something into a register from a memory location specified by the contents of a register. We are then essentially creating the bytecode according to the X86 64 definition, specification of how it needs to look to do what it should do. So this is, for example, a specifier which tells the system that it's working in 64-bit mode. Then we have the opcode. Then we have the actually specification of the scale and the memory, the scale and the source and the target registers here. Which I'm ORing with a 0. I, of course, wouldn't need that because it's 0, but I do that for my reasoning, because in other situations, there needs to be other values there which I'm using for ORing to create a specific scale there and stuff like that. It's just for me to be better readable. So then we are moving the destination register a little bit and putting the source register at the end, because register encodings are always 3-bit. And yeah, you can read all of that. You can read all of that in the specification. And if you when you see that, I guess you can think about why this wouldn't have worked as a live coding, because that is something that I didn't have in my mind. I couldn't just have written it down. I have pieces of that. I know something. I know how this looks basically most of the time, but I don't really know it really from the top of my head. So I really needed to read a lot and figure out a little, and I made some mistakes, and I needed then GDB to debug the stuff, and then I came back and said, okay, that's the wrong scaling there and stuff like that. So that's why I didn't do a live coding video of that, because I needed to figure all of that stuff out. Yeah, and as you can see, you can have different variants of that. You can, for example, not only put into a register the memory referenced by another register, but you could, for example, put a 64-bit immediate in there, and then you have a slightly different instruction set, instruction bytes that you generate. And you could, for example, move into the memory referenced by a register the contents of a register, which essentially is another opcode as well. So there you can see that this one is different, and of course the order here is a little bit different from the source and target, but this is simply another opcode. So this was 8B, and this is 8.9. So this specifies then for the system, for the CPU in the end, what it actually needs to do. And essentially for all of our things like add, yeah, like sub, and so on and so on, I implemented all of those bytecodes to kind of create the bytecode stream that we needed. And I always only, as you can see, have implemented the operand combinations and the bytecodes that we needed specifically to create what we are creating here. Yeah, it's not a generalized assembler. It has been written for this task specifically. Otherwise, I would have needed. I don't know how long do people need to write assemblers if they are not that versed in X86 64. Yeah, there is, for example, there is some calculation going on here then regarding with the jumps, because we need to calculate the relative position in the bytecode stream to where to jump, and then it's essentially quite easy to do that by simply emitting the corresponding bytes there, and the relative target with a specific little endianness byte encoding. And yeah, that works out in the end. So this call, for example, is quite simple. Emit return is mostly the easiest code of all. It's C3 simply. It's just the opcode C3, and you are done. Yeah, and essentially this thing is then, as you have seen, used by our JIT compiler then to assemble the corresponding instructions, like you would use mnemonics usually in assembler, because normal people don't write that; they write that if they write assembler. So and then the assembler is intelligent enough to understand what the operands are and what specific bytecode configuration there is, and then it creates the corresponding bytecodes, and then it emits the data there. And it calculates the jumps for you and stuff like that. But I wanted to do it on my own. I could have, of course, just generated something like that, so just the mnemonics, and then put them through, for example, NASM or something like that, and it would have generated the bytecode, but I didn't want to do that. I didn't want to use that. I wanted to do that on my own. And I had a lot of fun doing it, actually. I kind of removed a lot of my hair, which I don't have anymore, while doing it as well, because it wasn't that easy, actually. But I'm kind of proud of me to have actually been able to pull this off and to create something like that, because that's something I've really never done before, and it's a quite complicated topic, and I'm happy that I created that. And and as you can see, all of this whole module here is kind of conditionally included only on x86 64 Linux, and therefore you can actually execute this thing on a macOS, for example, as well, and it will use the interpreter. But it's not that meaningful anyway, because it's a Brainfuck interpreter. You usually don't have that or use that if you don't want to do something fun with it, which I now have. And I hope that you learned something from my explanations and my journey on how to actually create this thing and what I did for it and how it worked in the end, or how it works in the end. Please feel free to study the code on GitHub. Please, if you liked it, leave me a comment. Subscribe, give me a thumbs up. That always helps with the YouTube algorithm. And I'm happy to have taken this journey with you, and I hope to see you in the next one when we do a live coding again. So see you in the next live coding. Bye.